Okay, class, let's continue our discussion for Module 2, Lesson 2, in the first law of thermodynamics nga topic. So we are now in problem 4. So it states that a balloon contains 5 moles of a monoatomic ideal gas. As energy is added to the system by heat, say by absorption from the sun, the volume increases by 25% at a constant temperature of 27 degrees Celsius. So find the work done by the gas in expanding the balloon, the thermal energy Q transferred to the gas, and the work done on the gas. So let's have first the figure and data. So this problem, this is a non-flow process. Why? Because as what I have shown to you in part 1 for the first law of thermodynamics, a balloon is a good example for a non-flow process. So here figure and data. So now that a balloon, and then it contains 5 moles. So this balloon contains n is equals to 5 moles, and the next one, the energy that is added to the system. So of course it is exposed in the atmosphere. So we have the sun here, so exposed niya sa adlaw. So natay sun ara, which is the energy source. So gihit up niya ang balloon. Gihit up niya ang balloon, and the volume increases by 25%. Okay, increase siya by 25%. So therefore, if we have V1, for given V1, so V2 is equal to, since we increase siya by 25%, so that would be V1 plus 0.25 V1, or that is 1.25 V1. So that is volume 2. And then it states that this process is isothermal, because it's stated here that at constant temperature. So that the temperature before and after, so this T1 is equals to T2 is equals to 27.0 degrees Celsius. Okay, so isothermal. Then find the work done by the gas in expanding the balloon, because of course by looking at the balloon, so na siya mga air molecules inside, and of course once uh, this one gets heat up, so ang iyang mga molecules may exert of force on this flexible balloon, the walls of this flexible balloon. So syempre increase po ng pressure kaya ma-excite man ang mga molecules sa sulod. So ang required here, the required for this problem is the work done by the gas. So work done, next one is the thermal energy transferred to the gas. Of course we have here Q, and then the work done on the gas. Okay, work done on the gas. So work done, okay, on the gas, that is input. Work done by the gas in expanding the balloon, so that is output. Okay, so let's solve for this one. So again, na ay naatay diri this is the balloon, so we have here Q input man ta, and then sabi daw work done on the gas. So maybe na ay work done input, and of course find the work done by the gas in expanding the balloon, or that is the work being outputted, or work in the environment. Okay, that is the output work. Okay, so solution ta. Solution, since this is an isothermal process, okay, isothermal process, In isothermal process, we all know that U is 0. Why? Because U is a function of current temperature. So therefore, uh, from the first law of thermodynamics, okay, from first law of thermodynamics, we all know that Q, okay, the energy input, is equal to U plus work. So since this one is 0, so we have Q is just equal to the the work. Okay. So we only have kanang kan na tay given nga more na atong kanang given nga data. So since this is an isothermal process, so let's solve first for the work. Okay, solving for work. Solving for the work. So work at constant temperature, that is W is equals to um, this is equal to P1 V1 ln V2 over V1 V2 over V1. Okay, so this P1 and V1, okay, kan siyang P1 and V1 class. Actually, can siya kaya siyang P1 and V1. We can also express this one using using the ideal, okay, ideal gas law. Using the ideal gas law, we all know that P1 V1 is equals to MRT. Okay, so constant man, and this is also equal to P2 and V2. So therefore, we can express P1 and V1 equal to MRT, or in terms of moles, that is N, then R bar T. So pasabot aning bar is the universal gas constant. So we can use this since mao man ang given good nga so therefore our work now, W is equals to nRT ln V2 over V1. Okay, so mana siya ato ang work at isothermal. Okay, sunod ang next niya ni, okay, ato substitute ang values. So we have N, that is 5 moles, and then the value of a universal gas constant dapat kayo memorize mo ani na po ni sa cycle. So that is 8.31434, that is joule per mole degree Kelvin. And then next is the temperature. So the temperature here is 27. So 27 plus 273, dapat naka absolute na. Then ln of V2. So V2 is 1.25 times V1, kaya may increase man by 25%. That is 1.21 25 V1 over V1. Therefore, makancel siya. So simplifying this, and by unit analysis, atong kita ang sa units sa work. So here makancel ang moles, Kelvin makancel. So what's left is joule. So therefore, okay siya. Simplifying, we have 5 times 8.31434 times 27 plus 273, then ln of 1.25. So the answer here is 2782.94 approximately joules, or in terms of kilojoules, that is work is equals to 2.78 kilojoules. So this is the work. Okay, actually the work is just equal to the thermal energy that is transferred by the gas. So this answer here is just the same, because by looking at the first law of thermodynamics, Q is just equal to the work. This work is equals to Q. And what is this work? Actually, it is uh, equal to the work done by the system, and also uh, the work done on the gas. Kay para mo siyang ma-equate na siya. Actually, this is work output, that is the work done by the gas on the environment or the surrounding, and also this is also equal to the heat that is transferred into the body, and also equal to the input work. Okay, so same na siya. Anyways, mara siya gibaylo ra ba nga ang balon mi push sa outside, then mara pog ang outside mun counteract niya, so manang natay input pud nga work. And of course, same na ang answer, equal na sila sa Q, since this is an isothermal process. Okay, so let's proceed to the next. So here it states that a fully insulated piston cylinder contains 5 kg of air at 300 degrees Celsius. So natay figure and data. So can I see we have a piston cylinder arrangement. So this is piston. Then we have here, this is the cylinder, and this one is the piston. So mass here, and then it contains 5 kg of air. So therefore our mass here is equals to 5 kg. And then so here is mukantaglaing pen. So our mass here inside the cylinder is 5 kg, and initially at 30 degrees Celsius, and then at a pressure of 2 bars. So P1 is equals to 2 bars. Actually 1 bar is 100 kilopascal, so therefore this is 200 kilopascal. Then it expands from an initial volume of 20 liters to a final of 45. So therefore we have V1 is equal to 20 liters, and if we're going to convert this into cubic meter, that will be 0.02 cubic meter. Okay, motion conversion. And then V2 is equals to 45 liters, or that is 0.045 cubic meter. And as you notice, ang process niya, let's say it starts from this one, may expand siya, so therefore okay, there is siya. So can I see, and then next what happens is that this is 4.1, and then nagkaan siya, na-expand siya. So na-expansion hitabo man ang tawag sa process. So may expand siya. Okay, may expand siya. So ang molecules may spread out. Okay, so the behavior of the molecules inside, it pushes the piston upwards. Okay, may expand man siya. So this is 0.2. Okay, this is 0.2. So here, unsa man siya nga type of process? Is it constant volume, constant pressure, dili pod? And since it was stated here that we have a fully insulated piston cylinder, meaning we don't have heat energy nga transferred. So therefore, this process is adiabatic. Okay, adiabatic. Wherein we need to have K. So we need to have K is equals to 1.4. So that is for air. And of course, for an adiabatic, that is also isentropic. So S is equals to constant. So constant ay entropy. So if this is adiabatic, we're going to calculate the work done by the air and the final temperature during the process. So required for this problem, so we are required to solve for the work done by the air and the temperature during the process. So that is T2 pag humana. Okay, so let's solve. Ito na siya i-solve. So solution for an adiabatic process. Okay, for an adiabatic process, adiabatic process. So we have work is equals to 1 over this is 1 minus n, okay, multiplied by P2 V2 minus P1 V1. This one siya. And then we have P1, we have V1 and V2, but we don't have P2. So solving for P2 muna. So we all know, okay, we all know that P1 V1 raised to K is equals to P2 V2 raised to K. So therefore our P2 is equals to P1 then V1 over V2 raised to K. So at mo na ito i-substitute diri. Okay, so therefore we have here 1 over 1 minus K pala to. So dili siya N ha. So yung na siya and then substitute. So on the inside we now have sa sulod na natay this equal to 1 over 1 minus K. Then we have here P2, I mean V today. So we have V2, then P1 V1 over V2 K minus P1 V1. Okay, and we can extract pwede po na ito ma-extract ang P1 P1 V1. Okay, pwede na po or just P1 na lang. So si P1, so P1 on this one is equals to P1 over 1 minus K. Then we have V1 raised to K over V2. Then that is 1 minus K minus V1. And then plugging the values, so for P1 that is 200 kilopascal, so this one is 200 kilojoule per meter squared by 1 minus 1.4 for air. V1 is 0.02, that is 0.02 raised to 1.4 all over V2 is 45 to 0.045. Okay, that is for V2. And then raised to 1 minus 1.4, then minus V1, this 0.02. Okay, here since this is works, okay, kilojoules per meter, and then as you've noticed class, ang quadric kay cubic meter, so therefore makancel na siya, so magiging kilojoule meter na or newton meter. That's why energy ni siya ang work. So simplifying this, so we have 200 divided by 1 minus 1.4 times 0.02 is the power 1.4 all over 0.045 raised to 1 minus 1.4. Okay, 1.4, then minus 0.02. So we have here work of 9.40. That is 9.40 kilojoule meter, or that is ang 200 yan okay, kilonewton per meter square din siya. Di na siya kilojoule, kilonewton na siya. So makancel mo gyapon, so that is 9.40 kilojoules. So this would be the the adiabatic work. Okay, and then the final temperature during the process. So we already now have the work done. So manage ang work done, and then next is ato pangitaan ang change in temperature, that is T2. Okay, so solving for T2. So for T2 we have ano uh, ang temperature 2 ato ma-solve using katong baliktaning kani nga kani nga kaning relation, that is P1 V1 raised to K is equals to P2 V2 raised to K. And then we are going to, since ang given one day in terms of volume, so we are going to eliminate the pressure using the ideal gas equation, diba? From ideal gas we know that kanang PV is equals to mRT. So uh, if we're going to solve for P in terms of V and T, so that is P is equals to mRT over V. So this would be we're going to substitute this. So if we have here, it follows that P1 is equals to mR T1 over V1, or P2 is equals to mR T2 over V2. Okay, so we're going to substitute this one each here in our given equation in order to solve for the temperature too. Okay, kay given man ang mga volume, so tayo given other pressure, so manang ato iko ang equation nga in terms of volume and temperature. So substituting, this would be mR T1 over V1 raised to K is equals to mR T2 over V2, then V2 raised to K. So here we can cancel out this one, mR. So what's left? Okay, so in is we have T1, din karipod K minus 1 siya, so that is V1 K minus 1 is equals to T2 V2 K minus 1. So solving for the temperature, that would be T2 is equals to T1, then V1 over V2 raised to K minus 1. So ingon na siya class. So we are now ready to solve for T2. So T2 is equals to T1. So our T1 here is 30 degrees. So here 30 degrees. So don't forget again to change it into absolute. So we have 30 plus 273. This is in Kelvin. Multiplied by V1 is 220 liters is 0.02 and 0.045. So 0.02 over 0.045 raised to 1.4 minus 1. So here simplifying, the answer is in Kelvin. So 30 plus 273 raised to 0.02, 0.045 raised to 1.4 minus 1. The answer is 219. Okay, this one is 219.06 degrees Celsius approximately. I mean, that is not degrees Celsius. This one is in Kelvin. Okay, naka-Kelvin ni siya. And in degrees Celsius, so minus na nag 273. So kaya naka-Kelvin man ni siya. So the answer here is negative 1, negative 53.94. Negative 53.94. Okay, so basically yan na siya class. So let's try V1. Ato i-check balik sa P1 V1. Okay, si P1 there is K minus 1. So K minus 1 siya, and then V1 and V2. So muna na nga na siya sa second, and then napaday ko kaya dapit MR, so okay naman siya, then walang problema. And okay class, so let's continue. So the answer here is negative 53.94 degrees Celsius. So very kanagid below below freezing. So ingana na siya class kapag uh, mga problems that involves adiabatic expansion. So just derive the formula and just use the ideal gas law. So dapat always remember the PV equals MRT. So basic rigid kini siya dire. PV MRT. Ay gini kalimting PV over PV equals MRT. Okay, so let's proceed to the next one. Now we are on the second law of thermodynamics. So ang something nasa second law. So ang sa second law class is iyang gilimit ang definition sa first law. Diba? From the first law of thermodynamics, it is all about the energy transformation. So, diba? Energy talks about energy transformation. Now, in the second law of thermodynamics, mura ba siya tig pugong. Okay? Like kunyari, kaya mo na nga, okay, gusto ka malakaw niya, ako pugan kasi mong ginikanan. So, mura po din second law, mura po ni ginikanan ni first law. Okay? So, medyo na only siya kay marabag sa first law man god is, okay, mo mga processes, mo transform ang energy from one form to the other. But, there are some cases man god nga, ang energy transformation is diliingan nga 100% ma-transfer. Okay? So, mana ni siya ang second law. So, here for second law, na duha ka importante nga statement. We have the first one is the Kelvin Planck statement, and then the second is kay Clausius nga statement. So Kelvin Planck and kay Clausius nga statement. So again, second law of thermodynamics, mo limit siya kung say possibility sa first law. So ang ingon ni Kelvin Planck statement for second law of thermodynamics, ingon siya nga walay 100% nga efficient nga engine. Okay? Why 100% efficient nga engine? Kay, let's say, if we have an engine, so natin makina dire, specifically a heat engine, and if we have a hot reservoir, so if we have here a hot reservoir, of course, this hot reservoir has a temperature that is TH, and then since it is very hot, so it possesses high energy level, so high heat energy. And of course, this hot reservoir will go to the engine. Okay, meaning it inputs energy. Okay, input siya energy sa engine, and then according to kanang Kelvin Planck, since engine is man-made, so kita rin nagkuan na. So wala daw ko na engine nga 100% efficiency, because if that is 100% efficient, so therefore automatic, the energy that you input here would be equal also to the work, diba? We made engine so that it will do something that would benefit us. So therefore engine, it outputs work. Okay, work output. So therefore in this case class, if this is our diagram, from a hot reservoir ato siya convert fully into work output. So nindot kaayo ni siya. However, delete ni mahitabo because Kelvin Planck constant says that walay engine 100%, meaning kung sa imong gi-input tira ang energy, di na siya ma-equal sa imong output energy. Why? Because there's always kanang kuan negative losses yun. Okay, nadyoy nadyoy ma-excess. So therefore ang excess ana muna siya mga to sa cold reservoir. So Q cold. Okay, cold reservoir. So cold reservoir, this is TC. So again, based ni Kelvin Planck, walay 100% nga engine. So meaning, walay ingon nga kuan ha. So ang first nga assumption ato isuwat nga uh, energy in is equals to work output. Okay? Wa na yung ana. Pero na ano ay energy in is equals to work output plus sa energy nga na waste. So naay ani. Wala yung energy in nga ma-convert ang all energy nga mag-input ma-convert that into output work or useful work. Okay? Wala yung na because di ba ganiha we also talk about entropy, so na ay random disorder. Okay, so kung na random disorder meaning nag-waste nga energy pud. So mana siya importante sa Kelvin Planck nga kanang statement. The second statement pod kaning kay closures. Okay, kay closures importante man siya. Why? Because kanang ang closures nga statement ingon pud siya nga kanang walay engine or kanang walay device nga nag-exist. Let's say if we have here an engine or a device, so or engine lang gyapon nato, and then working from this one is the hot reservoir, so this is hot TH, and then this is a cold reservoir. Okay, cold reservoir, this is TC. Okay, so wala daw ko na engine sa tibok universe nga i-convert niya ang cold temperature. Okay, convert niya ang cold temperature to a hotter kanang temperature. Okay, directly to the hotter temperature because di ba ang normally, okay, ang normal gud hitabo kay ang hotter object, okay, will become colder, di ba? Mao na natural process. Ang hot mga to sa cold, pero why ingon ni ang cold mo init kay if mo na siya din wala kay laing gi-apply, now it will violate the laws of thermodynamics. So kan siya violate na siya because in order to make this diagram works, so dapat according to closures na kay input nga work. So if this is our engine and if this is our cold reservoir, okay, cold reservoir TC, and then misod siya sa engine, and then output siya sa hot reservoir, so meaning output niya kainit. So hot reservoir, that is TH, so init na nga to. So in order to work this, so dapat na jugay i-add nga energy. So dapat you must have input here, so that is work input. So if you have an input work here, so man maka-bring ka sa colder body into a hotter body. So kani this one would definitely work. So man siya, ano yung tigaman for kuan sa second law of thermodynamics kaning kang Kelvin Planck o kang closures. Again for Kelvin Planck ingon siya nga way 100% efficient nga engine. Kang closures pod di ba ka pwede pataka-takag convert from a colder body imo siya i-transferred or i-become into a hotter body without any work input. So dapat na kay i-input nga work kay ang natural ang process ra nga mo-exist kato natural process nga ang init mo bugnaw, dili ingon nga ang bugnaw mo init dayon naturally, kailangan kag naa kay i-input nga work. So in the second law of thermodynamics naanantay upat ka mga kuan importante nga formulas nga dapat ninyo makanan, because since we're talking about efficiency here and we're dealing with engines, so let's start our discussion for second law with the pinaka efficient so far mo gini ang pinaka efficient nga ma-attain sa atong mga makina. We are going to call this one as the Carnot engine, and this Carnot engine is associated with the famous Carnot cycle. So mo rin siya ang pinaka most efficient na cycle or engine. Okay, nga ma-attain ni gid ha, ma-attain. But of course, ang actual nga mga makina nato below the efficiency of the current cycle, because this is just our basis ha. Even our basis, or even sa kaning atong gibasihan kaning current cycle, di magina siya moabot og 100% efficient. So mao nang gagandi tag losses na ini. Okay, so man siya mo na itong basihan para ma-analyze kung unsa ka efficient ang atong engine nga exist today. So kanang mga atong mga internal combustion engines. So let's start with the Carnot cycle. So the Carnot cycle actually follows four processes. So if we're going to kanang to plot this on a TS diagram, so TS. Now the Carnot cycle will look like this. So yung ani ang graph sa Carnot cycle na ay constant temperature nga heating sa from 1 to 2. Okay, then from 2 to 3 na ay expansion, isentropic expansion. Okay, diba straight line entropy. Then 3 to 4, that is isothermal cooling, and then from 4 to 1, that is isentropic compression. So in process 1 to 2, again, and if we're going to plot this one on a PV, so siya, this is a cycle. Okay, kanya itong mga lines man siya ang path. These points represent the state of our working substance. So ang atong working substance ini mostly air. And then next one is PV. PV. So in the PV diagram, the shape of this kay nga ni siya. So for PV, man siya, muna siya kite. Ana, and the next ana, and then ana. So here we have 1 to 2 at constant temperature. Then next 2 to 3 is na ay isothermal expansion. Then 3 to 4 is isentropic expansion, isothermal cooling. Then 4 to 1, that is isentropic compression. So again, natin isuwat, we have process 1 to 2, that is isothermal heating, meaning we add the heat. So ato i-label dira, ato butangan, we have Q added, QA, or we have QH, because this is the hotter temperature. Kayong babaw mo na siya T hot, init na yung temperature diri. And of course, the kaning nas ubos, this is T cold. Okay, so 1 to 2 isothermal heating, then 2 to 3, that is isentropic kay vertical line man. Isentropic o adiabatic po siya. Isentropic expansion. So yung sa expansion, may increase ang volume. So may expand man. Isentropic expansion. So 2 to 3 na siya. Then next we have 3 to 4. And the expansion pod, sa expansion actually, napodra ang output work nga mahitabo. Okay, napodra ang work output mahitabo. Workout. And then of course, in the isentropic workout, and then 3 to 4, that is isothermal again. Isothermal cooling. So nganong cooling man, so if notice here, isothermal kuan din siya, heat absorption. Yun siya, yun nga cooling. Kaya isothermal naman. So isothermal heat absorption. So nga namang absorption because it absorbs heat. Okay? I-absorb niya ang heat. So the absorption, sorry. Kana siya isothermal heat rejection. Isothermal heat rejection. So iyang gi-reject ang heat at low temperature. So nagpagawas siya heat. So Q O or Q low. Okay, at the uh, cold reservoir. Mubalik na pod siya, i-compress na po siya balik. So na po diri for process 421. Process 421 is known as the uh, isentropic compression. Okay, so gi-compress siya. Of course, dapat ay input nga work ara. Diba? If kung mag-compress ganita, we need to have an input work. Okay? And in the Carnot cycle class, actually, the difference of the output and the input is what we call as the work net. So work net is equals to work output minus work input. So mana siya ang work net na to. So just a word to remember. And here we're going to derive the efficiency. The efficiency of a Carnot cycle. So the efficiency of a Carnot cycle, so again, efficiency is normally E, defined as the energy output, okay, energy output all over energy input, okay. So ang output here is the network, okay. So mara siya ang marag final output na gud ba kay di man ta pwede ang work output sungod kay dapat ato pat na i-subtract sa work input ari kay nagbutang biabot ta diri trabaho, so therefore ta na i-subtract mo ng work net ang tong gamit sa energy output. So efficiency, that would be work net, okay, work net all over the energy input here is QA or Q hat, okay, Q hat. And what is work net? So my work net na now if we're going to draw a diagram for this one for the Carnot cycle. So if we have here an engine, and then we have a hot reservoir TH, and then next one cold reservoir. Okay, gi-reject niya ang reservoir sa kuan gi-reject niya ang heat sa cold reservoir. So here ang output sa engine nga gi-deduct na sa input. So that would be our work net. So ano nang work net diri? Work net, so miso dira ang QA. This is Q added or Q hat na lang. Then migawas pod ang Q cold, that is QC na lang. Okay. So here, by taking a look at the engine, so ato iko ng law of conservation of energy, that is energy in equals energy out, diba? We'll know that at the engine, okay, at the engine, we'll know that energy in equals energy out. So from the point of view of our engine, ang energy nga misulod kasi QH is equals to energy out, that is ang work net plus QC. And since we have work net here, so we can derive work net para makuha na to. So therefore work net is equals to QH minus Q cold. So substituting that one, kani mahimon na siya og QH minus Q cold over QH, or this is also equal to 1 minus QC over QH. Mano efficiency sa ato ang Carnot cycle if given ang energy at the kanang hot reservoir o energy at the cold reservoir. How about kung temperature ra? Can we have a formula for efficiency that is in terms of temperature only, the hot reservoir temperature or the cold reservoir temperature? Of course we can do that. Now take a look at the TS diagram. Unsay formula sa atong Q diri? Since we have Q here, what is the formula for Q for an isothermal? Diba? You have a lot of formulas, but let's use the entropy na principle. So by entropy, by entropy, we know that Q is equals to TDS or DQ. Okay, mo na ato and this can also be written as T is equals to T delta S, or that will be T S2 minus S1. And we're going to apply this one here for our efficiency. So applying this one, so we have here Q hat is equals to T hat multiplied by the change in entropy here. That is from 1 to 2, so that would be T, that is T hat, TH, multiplied by S2 minus S1, plus, minus di. So, i-subtract na siya. Minus QC, that is T cold. T cold na. So, T cold na siya. T cold multiplied by the entropy, that is from 3 to 4, so that would be S4 minus S3 all over the QH again is T hat times S2 minus S1. Okay, here we all know that in the diagram, that is from the diagram, ang kuanra na equivalent nga si S3 is equals to S2, kay asymptotic ba, same ilahang entropy, and also the same with S4, that is equal to S1. So substituting this, magiging TH S2 minus S1 minus TC, then S1 na siya, no? So S1 minus S2. Okay, so mana siya, S4 minus S3. So S4 minus S3, or since this is kuan di, sorry, so mag negative na yung answer ni kiton kay mas dako biya si S3. This one kuan diri is ang difference, that is S3 minus S4. So here S3 is S2, that is S2 minus S1, then divided by TH, then S2 minus S1. And then as you notice, na-dyan makancel, nara makancel S2 minus S1 here and this one. So therefore what's left is our equation for our efficiency in terms of temperature only, that is T hot minus T cold all over T hot. So that would be the other expression for efficiency in terms of the temperature in the hot reservoir and the temperature in the colder reservoir. And if you're going to solve for the work, to just use the Q instead. So meron siyang efficiency sa Carnot cycle, and meron siya maximum efficiency ka mating. So basically maragin ang Carnot cycle, and let's proceed to the heat pump. So ikadua ang heat pump. So kaduha heat pump. So unsa may nasa heat pump class? So for heat pump, okay, heat pump. So for heat pump, let's say we have an engine. And then we have a colder area here, or a colder body. Okay, and we label this one as T cold TC. And then by closures, mag-input ko energy sa engine so that I can produce an output energy nga magamit. So let's say ako ni siya ngadto sa room. Okay, the purpose of heat pump is to add kanang energy to an existing system nga mo increase yung temperature. So here this is our hot reservoir, so that is TH. So maybe gigamit ni for house heating or home nga kanang heating device, so mainit ang kan during winter, so gamit ka ng heat pump. So ang flow sa energy niini from the engine to the hot reservoir. And of course, gikan sa cold reservoir pod from sa engine. And of course, we have some input energy here. So atong inputan diri og work input. Okay, for a heat pump class, ay ang importansya na ni since ang output sa heat pump for the heat pump we are after with the hot side. Mo na yung output nga maka-output siya init ba? Init mo na siyang heat pump. So therefore, in order to solve for the efficiency, its efficiency, that is E is equals to Q output over Q input. So here the output is actually TH. So in terms of temperature, that is TH all over unsa man nato ang gi-input, that is W in kaning work. Ano man ang input atong system, W in manag input. Okay, input work, and we all know that the input work is just equal to T hot minus T cold. Therefore we can equate this one as T hot all over T hot minus T cold. So in siya class for the kanang kuan, this is for the heat pump. So this is the efficiency of a heat pump. Actually kanang kuan po din siya matawag nga kuan, this efficiency COP. This is the coefficient of performance because the answer here for the COP actually di tama ka nga efficiency, tawagan natin COP na lang. Okay, this one is COP. So COP sa heat engine, okay, COP sa heat engine is greater than 1. COP is greater than 1. So magana siya T hot over T hot minus T cold. That is for the heat pump. Kaya ang goal sa heat pump is to collect the hot side. Yung utilize ang hot side. How about for the next one, ikatulo. Ikatulo, we have here the refrigerator. Okay, for the refrigerator, again we have an engine. Diba the reason why mukol ang refrigerator is kuha natay gidagan na kuan working substance nga mo extract og kanang kuan energy ito sa tong food nga refrigerate para mabugnaw pagid siya. So here we have an engine and we have a cold reservoir. Okay, cold reservoir TC. Then of course another hot reservoir na pod. So here we have hot reservoir, that is TH. And here para ma-bring ni siya from a colder state, okay, into a hotter state. Now we're going to add we're going to add energy. Okay, para dito makavalid sa kay closures. So add energy, that is work input. Now solving for the efficiency of the refrigerator. So unlike heat pump ang importante nga side sa heat pump kay ang kanayahang kuan mo-produce siya og hot air for air or other substances. So man yung goal. But for refrigerator is opposite. Ay output ani is kaning cold air dere or ang cold na side kaning bugnaw sa ubos. Mo na siya ang goal sa refrigerator. And in order to achieve that, we're going to input energy. So therefore the efficiency for this one, that is E is equals to output, work output over input, or output work over input. So here the output work here is kaning T cold because mo na ang goal. Okay, T cold. For refrigerator, ang cold side mo ay gihimugatan. So that's why we have here ano, T cold. T cold all over. This one is T hot. T hot minus T cold. So, yan na siya class. And then as you notice, katong ikanon ang output. Okay, so ang output init T cold over kanang T hot minus T cold. So basically, nga na siya. Mana siya efficiency for a refrigerator. Kani siya. Okay, so let's resume class. So actually, kaning COP sa heat pump, kasi nalibog mo kani ato na kuan ato ni Osborne. Actually, this is work input. Because diba, that is output over input man. So ang input ani kani mong work. Muna yung input work and also this one input work. So mo gini ang na-address sa ubos. So this would be work input. So that would be work input. So here we're going to relate the COP. Okay. COPH ato ni can denote ni lang duha. Actually this is not efficiency since this is greater than 1. So we just label this as COP. So COP sa heat pump. This one is COP sa ref. So if we're going to modify the COP for heat pump, we can also say this that this one is COP sa heat pump is equal to T hot minus work input, and we all know that T hot is equals to T cold plus work input, then all over work input. So separating this, we have T cold over work input plus work input over 1. So can I share this will be equal to 1. So we now have T cold over work input is T hot minus T cold plus 1, and we all know that this one right here can I see T hot minus T cold is just equal to the COP of the refrigerator, COP rep. So therefore the relationship between the COPs of our heat pump and the COP of ref is that COP of heat pump is equals to COP sa refrigerator plus 1. So mara ni siya class ay mga formulas nga may remember for heat engine and for a refrigerator. So again, heat engine gamit kani especially for winter kay ang hot side man may importante nga maka-produce og kanang hot air. And for refrigerator, importante ang cold nga part since para makastore ta og kanang mga foods in a very long time. Kay mo freeze man na siya. So therefore, mo na siya ang mga importante nga formulas. And COP can also be kani siya pwede po ka mga gamit aniha for in terms of the heat that is equal to Q hot. If given ang heat energy, so Q hot na lang over Q hot minus Q cold. Okay? More na yung gamitan, and then the same thing with the refrigeration, that will be equal to QC, this QC, so based from this one, so divided by TH minus TC. So more na siya in terms of input energy. Okay, so let's answer some sample problems. So the first one states that one of the most efficient engines overbuilt is a coal-fired steam turbine engine in Ohio River Valley, driving an electric generator as it operates between 1870 degrees Celsius, okay, and to 430 degrees Celsius. So let's say mao ni ang pinaka-efficient pero mas equal ni or mababa pa gini sa siya sa Carnot cycle. So this is our engine. Then we have a hot reservoir. Okay, this is the hot reservoir, and of course this hot reservoir, ang iyahaan ning value TH is equals to 1870 degrees Celsius. Hot reservoir, so mga ito na siya. Okay, hot reservoir, so paubos siya. Tawad aning hot reservoir, gigamit siya para makaproduce siya output sa makina. Okay, na kay how much daw does mechanical power does the engine deliver, so absorb. Then output niya is ito ng tubig, so output ani sa engine. So this would be the cold reservoir. Okay, so cold reservoir. Okay, so in a cold reservoir, the temperature is, this is for kanis, yeah, TC. Okay, so kanang siya TC. So TC, so we have TC is equals to 430 degrees Celsius. So 430 degrees Celsius. So nalatay duha ka mga data, and I think it is enough already. So what is the maximum theoretical efficiency required? Required for one solve for max efficiency. Okay, so in order to do that, we're going to use the Carnot cycle. So let's solve. Okay, this Carnot cycle na itong basis mo, kay mura siya may pinaka maximum efficiency. Okay, so solution, this is an engine, so naging siya output. This is work output. So solution here, gamit sa Carnot efficiency, since ang given kay mo ang temperature, so i-temperature na nato, so that would be a solution. So we have efficiency E is equals to T hot minus T cold all over T hot. So T hot is 1870 minus T cold is 430 all over T hot. So T hot here is 1870, so since si T hot nag-usa sa ubos, so dapat mag-add ka dig plus 273. Okay, so here the efficiency of this car E is equals to, that is 1870 minus 430 divided by 18 divided by, so ito na i-divide 430 divided by 1870 minus 430 divided by 1870 plus 273. So the answer here is 9 over 13. So the efficiency is 0.69. So the efficiency here is 0.69, or approximately na siya, or approximately 69%. So yan siya class. And then how much mechanical power does the engine deliver if it absorbs? Okay, kung naka-absorb na siya o kanang kuan, if it absorbs 1.4 times 10 to the power of 5 joules of energy each second from the hot reservoir. So that would be our Q hot. So yung balik na siya. So Q hot, QH. So muna siya ato ang input, and then ipangita ang mechanical power. So when you say mechanical power class, that is just uh, the same with the kanang kuan mechanical power, that is just equal to the work output W out. So ikaduhang na pangitaon is W out at certain conditions. So in order to solve for that one, we are given QH. So we have here QH. QH is equals to um kanto siya kung iya daw actual efficiency. So QH here is 1.4 times 10 to the power of 5 joules. QH is 1.4 times 10 to the power of 5 joules, and it has an actual efficiency of 42%. Then how much is the mechanical power? So if find the mechanical power, so that is work output, so that would be W output. Okay, in order to solve for W output, just look at the formula for efficiency, that is E is equals to the work output over input is QH. Okay, so deriving work output, so that is work output equals to E QH. Okay, and we know that E is 42%, so substitute, we have 0.42 multiplied by QH is 1.4 times 10 to the power of 5. So the answer here is 0.42 times 1.4 times 10 to the power of 5. So that is 58.8 kilojoules na noon. This one is 58.8 kilojoules. So this would be our work output. Okay, so muna siya class. Muna ito ang work output. Okay, muna ang work output and the efficiency. So let's proceed to the next one. A heat pump daw has a coefficient of performance of 3.8 and operates with a power consumption of 7.03 times 10 to the power of 3 watts. How much energy does the heat pump deliver into a home during 8 hours of continuous operation? And how much energy that does it extract from the outside air in 8 hours? So we have a heat pump. So ato na po dito ang heat pump. Let's say this is a heat pump, and then ipagawa siya sa kanang hot reservoir, that is TH, label TH. Ayan na episode niya nga cold reservoir, gikan sa cold reservoir. This is the cold reservoir, this is TC, and then ma-flow na ato. Of course, syempre dapat yun na ay work input. Okay, we have here an input work or the work net. Okay, so we have W in. So that is the input work, which is equal to the difference between the hot reservoir and the cold reservoir. So here we have a given given nga COP sa heat pump, that is 3.80. Then ang power consumption, when say power consumption class, muna ang input nato nga work or energy. Work input is 7.03 times 10 to the power of 3 watts. Masya. And then kanin siya at 8 hour operation, continuous operation. So what we need to do here is the work input in terms of kilojoules na lang, ato siya multiply of 8 hours. Okay, that would be 7.03 times 10 to the power of 8. Then multiply na 8 hours. So diri mo gud ang iyang unit kay watt, that is joule per second. So this is 8 hours. So we have 1 hour is equals to 3,600 second. So makancel na siya. So here makancel po ni secondary so what's left is r na lang yun. So simplifying, we have 7.03 times 10 to the power of 3 multiplied by 8 hours times 360. So the answer here is in in joules, but in kilojoules lang. That is divided by, okay, ang power consumption is this to the power of kanina, this to the power of 3 ra na 8 man nun dire. So kanina siya 3 ra na siya. Okay, so again ato i-calculate og utro. So kanina siya to the 7.03 times 10 to the power of 3. So ang answer is for 8 hours, 8 hours of continuous operation. So answer would be this, and then divide by 1000. Tako jud gihapon. So our input di ay atong input is W input is equals to 20.2464 kilogram. Okay, I mean kilojoules pala. This one is in kilojoules. Okay, and then how much how much energy does the heat pump deliver into a home during the 8 hour of continuous operation? So again, atay ikuan ini is ang Q hat, anti hat, I mean ang Q hat di ay kay mo man nagipangita. So ang required po din required is Q hat. Kay mo na how much energy does the heat pump deliver into the building during 8 hour of operation. So Q hat, and to solve for Q hat, that is Q hat is equals to work in plus QC. Okay, that is the current temperature in the cold reservoir. Okay, mana buka sa Q hat, but we only have COP. That is COP divided sa COP sa heat pump. That is equal to the output, which is our Q hat, over our input, which is WN. So therefore, atong Q hat dire, so Q hat is equals to work input times the COP. Okay, the work input muna to, that is 20.2464 kilojoules multiplied by the COP 3.8. So ang Q loss nimo times 3.8, that is kuan na siya 76 7 million day. So we have here 7,693 62.2, so 76,000 mana siya. Then ang kwan is in kilojoules. So basically klase nga na. And then B, how much energy does it extract from the outside air? Okay, gi-extract niya from the outside air in 8 hours. So that would be Q saman, that is QC. So to solve for QC, since na naman tani, so to solve for QC, use this. Ito nang gamiton. That would be QC is equals to QH minus work input. That would be the input work. Okay, after 8 hours na siya. After 8 hours is ang QH so QH is 76,936.22 minus work input is 20,464. So that is minus 20,464. So the answer is 56. Mana siya at the code reservoir is 566,899.2 kilojoules. So this would be the heat on the outside surrounding. So mana siya class. 10 watts the joule per second. So 8 hours, 1 hour, 2,600 seconds. So cancel siya and mana, so manindoha dagko kaayo ang value. Let's proceed to the last one. This is for the refrigerator. So a freezer has a coefficient of performance of 6.3. So another siya COP, a freezer. So let's say this is our freezer or our ref, and then of course it has COP. It has COP is equals to this is for ref is equals to 6.3. Then the freezer is advertising as using 457 kilowatt per hour per year, kilowatt hour per year. So meaning money hot reserva, this one is TH hatag siya, and then the other one ang cold reserva hatag po sa freezer. Of course si freezer nagkuan po nagpatakbo sa logistic. So we have here input. Okay, and we can also have here, this is also equal to kuan. So kuan siya, this is also equal to Q hot then Q cold. Siya class. Kaning gingan niya, the freezer is advertising using 457 man siya ang work input. That is work input is equals to 457 kilowatt hour per year. Okay, so on average how much energy does the freezer use in a single day? So pila may use sa freezer. So it talks about the QC kay mo ni ang freezer nga part in air conditioning kani mo ni ang freezer. So mo na siya ang freezer nga part, and ato na i-calculate ara kung pila. So for the freezer you just use the COP, diba? Formula for COP is equals to that is Q cold mo importante over the input work, that is W in. Okay, this is for ref. So QC is equals to COP sa ref times the input work. So much for QC. Then imo lang i-multiply. So COP is 6.3. So we have here 6.3. The work input is mana siya 457 kilowatt times R over a year. So here butan mo 1 year 365 days, then 1 day, 24 hours. Okay, 24 hours. So here makancel siya the or per year na. So on average how much na is removed from the freezer each day. So kada adlaw man, so per day ni siya. So here kutob ta diri na lang 1 year 365 days. So ano ning usa kay naam gini siya per day because makancel na mo dira ang R. Okay, here it will be like this, kilojoules per second times the height. Kaya, I mean, ang kilowatts is kilojoule per second times the R pala, I mean. So, therefore, ato pa sa na-convert sa babaw into second. So, it will go this way. Since nababaw ang R, I mean, ang second, nasa ubos. So, ang kanan is, we have 1 R that is 3,600 seconds. So and plus this would be 1 year. So cancel ni. So we have now this one R pod kani siya R cancel, and this one is kilowatt is kilojoule per second, so makancel per second. So what's left is only kilowatt per day. Substituting 6.3 times 457 times 1 over 365 times 3,600. So we have 28 QC equals to 28,396. That is 28.396 396.60. Okay, mana siya ang QC. Then what maximum mass of water at 20 degrees could be freeze in the freezer in a single day. Okay, so it talks about the QC. So mo freeze man siya, diba kanay man within this nadra ang responsible for freezing. So unsa may energy nga nadra, that is QC. So we can equate this, that is QC is equals to mass sa water. Dapat ato pa ang temperature sa water from 20 degrees to ice, that is 1 degree. So that is mass of water, CP sa water, delta T. So here ipangita is the mass. So namatay CP sa water 4.187, therefore we can solve for M. M is equals to QC CP delta T. QC is 28,396.6 divided by CP sa water is 4.187 kilojoules per kilogram Kelvin. So kaning asa diri sa QC, actually ang iya anin diri operation is kilojoules per day. Kilojoules per day. CP then delta T from 0 final is 0 to 20. Okay, 0 to 20 degrees, so 20 minus 0, so that would also be equal to 20. Okay. Kaya delta T man, so that is from 20 to 0 degrees. So ang difference kay 20. So simplifying, anyways makancel man siya. May kilojoules makancel. Then next one is kani siyang Kelvin, at Kelvin po yun diri, so makancel ni. So per kilogram na lang anya giingon ba diri, maximum water could be placed in a single day. So amount so ang answer diri is kilogram per day. So the mass now is equals to, may mo na siya og 2 839 2396.6 divide by, so divide by 4.187 times 20 times is 339.10. That would be 339 339.10 339.10 kilogram per day. So mana yung makaan, class. So mana siya, class, for this problem number 3, and I hope you learned something, and thank you for listening. God bless. Ha?